Welcome back, ladies and gentlemen. This is the second video that I want you to watch that talks about angled projectiles. The first video was talking about what happened if I had something on nice level ground. And honestly, it makes a lot of sense. You go through the same procedure you do for any kinematics problem. You just add the extra step of breaking something into components first to figure out the x and y initial velocities. Then you just do the same work you did before. All right? Now, the next two questions are the final piece of the puzzle for projectiles. And that is, what happens if I have an angled projectile that is not on level ground? All right. Now, I'm going to tell you that I'm really excited because this is going to be the most intricate solving of equations you're going to do all year. I'm willing to bet that most of you have already looked at this video and have started shuddering at the fact you see the quadratic formula. Do not worry, you will be okay. But it's going to be very important in this particular question because it's going to be necessary to solve for what we're looking for. All right? Now, we start, like we do with all these questions, by trying to figure out the components of the velocity. All right? So let's take a look at this question first, then we'll break down the components. It says a ceramic ball is launched from the edge of a 1.5 meter table. The initial velocity of the ball is 3 meters per second at a 20-degree angle. All right? When in doubt, the easiest thing to do, honestly, is to draw a picture of it to help you visualize it. All right, and I've done so just to the left. So you see I've got a 1.5 tall table, and I have a cannon that is designed to launch at a 20-degree angle, and it launches at a velocity of 3 meters per second. All right, now, we're going through, we're going to do some kind of launch stuff. So our next piece is we say, all right, well, it's not very useful that it's at an angle, so let's reimagine it as its vertical and horizontal components. And you'll see, I've already kind of done the work down here to work through it, but you get the same idea we talked about before. You break into horizontal and vertical components. The horizontal one is going to be the launch velocity times cosine of the angle. So launch velocity times cosine of 20 degrees. The vertical component, launch velocity times sine of 20 degrees. So you go through, calculate those two things. And if you break it into components, you get that the x velocity of the cannon, of, I guess, the ceramic ball, the cannonball, whatever you want to call it, is 2.82 meters per second. The y velocity is about 1.026 meters per second. All right. Now, for the fun part. This question has two parts to it. The first question is, how long will it take to hit the ground? So it wants to know how long will basically the ball be flying in the air. Well, even though this is an object that is being fired at an angle, and it is not just a horizontal projectile, the same rules that we applied in our lab still apply here. So you need to use a Y chart to figure out the time of flight. All right. If we go through and we fill out our chart, we have a few things that we can put in there. All right. We start with the initial Y velocity. Now, so far when we've done questions like this, it's been a horizontal launch, so the Y velocity has always been 0. This is not a horizontal launch, which means that I actually have an initial y velocity. And that initial y velocity is the y component we just figured out. So VI is going to be 1.026 meters per second. All right. Now, this, of course, is an object that is in free fall, so we can assume that its acceleration in the y direction is going to, again, be negative 9.8. All right. And the third piece of the puzzle, delta y. All right. This is something that at first might seem strange, but I promise we have to remember what the definition of delta y is. Delta y measures the change in y position. It's not measuring the total y distance, it's just measuring the difference between where it starts and where it ends. And because of that, if we look at our drawing, we see that because the height of the table is 1.5 meters, the delta y for the ceramic ball will end up being negative 1.5 meters when all is said and done. So, I now know three things, and I want to find this fourth thing of time. All right? So, I look for the formula that has VI, AAT, and delta y. The formula that has that is this one. Now for the fun part. If we plug in our numbers, something happens that has not happened to us before. And that is that first VI term is still there. Usually we've gotten around it by saying VI is 0, so we don't have to worry about it. But today, we don't have that luxury. All right? Now, This is where all that work you've done in math class and all those different equation solving things that had no context come to light. Because what you can do is you can solve for t in this little complex equation. So what you need to do is, again, in order to make things neat and nice, I like to put everything in order just like this. You know, you have your square, then just your normal term, then 1/2, and you get it all equal to 0. The way to solve this, because unfortunately this does not factor nice and neat, is you have to use that wonderful, amazing formula, the quadratic formula. All right? This is why at the very beginning of the year, when I gave you your first homework, one of the things I had you do was solve using the quadratic formula. This is why. Because this exact setup of a question utilizes that technique. All right? So, the quadratic formula, for those of us who aren't sure or don't remember, which happens, I had to look it up because I don't remember it, is negative b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. For those of us who don't remember, the a, b, and c come from the numbers in front of kind of these terms. So remember, a is right here. That a, so negative 4.9 is a. 1.026 is going to be b. 1.5 is going to be c. So you take those three values, you plug it into the quadratic formula. Now, this is going to be something where you're just going to have to practice doing the calculation. All right? You go in there, you plug in the numbers correctly, and you will get two different answers, as you should, because remember that plus minus in front of it means you need to have two different answers for t. The way you pick the correct time is you notice that in your two solutions, one time is negative, one time is positive. Since time cannot be negative, that tells me, oh, I guess I need to pick the positive answer. All right? So I want you to take a moment to pause the video, and I want you to work through and try and show that the time it takes to hit the ground is 0.67 seconds. So if you're kind of working through it and I'm going too fast, pause the video, work through the question at your own pace, and when you're ready, unpause it, and we'll talk through the next part. All right? So, if you've worked through it correctly and you've solved kind of your equation, you'll get that the time of flight is 0.67 seconds. So right there, you finished the first part. Now, for the next part, it's even nicer because you're going to do the exact same thing that you did for your lab. The next question is, how far does it land from the table? So it wants to know delta x. All right? Well, to figure that out, we need to know a few things about the x motion. And we already know most of these things because we figured them out. We figured it out when we did our components. So the velocities in the x direction are going to be the same, and they're both going to be what that x component was, 2.82 meters per second. And again, that's coming from when we did our work over here, and we broke the launch velocity into its x and y values. Again, this also is in a state of free fall once it leaves the cannon, so the acceleration in the x direction is 0. And the time is now going to be what you figured out in the first section, because that is what links the y and x motion. Because of that, I now know everything I need to solve for delta x. So you go through, you write out this equation, delta x equals the x velocity times time. You know these two things. And you'll get, when you all said and done, that the x range, how far it goes to the right, is going to be 1.89 meters. Now, again, if you're like, I don't really trust that, or I'm not really sure I did it right, open up that little simulator that we did in the lab, set it to the parameters of this question, and see if your numbers match up. Because that's going to be a perfect way to kind of visualize and figure out if you did the calculations correctly. All right? So, if you're still working through it, pause the video at this point, just kind of work through the answers, have the work in front of you, practice it. Once you feel confident in that question, go to the next one. All right, and we'll practice, and we'll go through the next part and practice this again. All right, so the first question kind of introduces us to how to use what happens or how to use the tools that we have available to solve for something where it's on top of a cliff or it's not on level ground. This question is the same thing. It has a little wrinkle thrown in there though, which is awesome. I really like it because it forces you to have to think about what pieces of information you have available to you. Okay? So, we start with a canon, which this is such an anachronism, but I guess whoever wrote the question, I did not write the question, I stole it from somewhere else. All right, I guess King Arthur is magical enough that he has invented gunpowder. All right, so his knights fire cannon from the top of a castle wall. Now, the cannon that they fires a cannonball at a speed of 50 meters per second at a 30-degree angle. Now, they're also, at the same time, on the top of the wall, someone was startled and they dropped a cannonball, all right, which means it only traveled in the y direction. It took 1.5 seconds for that cannonball that was dropped to hit the ground, all right? Now, just to kind of help you visualize, we go through to our lovely little artwork as well. We'll just kind of draw this. We basically have this castle wall, all right? We have our cannon. It's going to launch at a 30-degree angle, so boom, and at the same time, someone dropped a cannonball that just went straight down. All right? Now, again, the first thing we do is we need to break stuff into components. All right? So I take that launch velocity and I break it into components. Same process as before. X component is 50 cosine of the angle. So it's going to be the launch velocity cosine of the angle. So 50 meters per second times cosine of 30 degrees. The Y component is going to be the launch velocity times sine of the angle. So 50 meters per second times sine of 30 degrees. Once you do that, we can start to kind of write our charts. So the question is, how far from the castle wall does the fired cannonball hit the ground? So we want to figure out delta x, all right? So that means we need to write down an x chart. And I know, I apologize, there's a lot of stuff going on here, but we just kind of think about what we use to solve for certain things. So with maximum range or how far it goes, we usually use an x chart, all right? Now, in the x chart, there are some things we can fill out. We can fill out the launch velocities. We know both of them. It's going to be the x component of the velocity. And we also know the acceleration of the cannonball. It's 0, because again, there's no x forces, and there's no horizontal forces acting on the cannonball. Now, I have the time covered up, but you don't even have that luxury, unfortunately, because you'll notice there's nothing in this question that says how long it takes for the cannonball to hit the ground. So you're actually left with a problem, because even though you have 3 things in your chart, this is the one very unique thing about X motion. You actually have to know the time of flight before you can figure out anything else, like delta X. That's just a weird quirk about X motion with projectiles. What that means is that I'm a little stuck because I don't know the time it takes for the cannonball to hit the ground. All right? Now, I know I can find that using my Y motion, which, that's the next thing we'll do. So we draw a Y chart, fill it out with what we know. So when we do our Y chart, we know the initial Y velocity of the launched cannonball, 25 meters per second, because that's 50 sine of 30 degrees. The acceleration, again, it's in free fall, negative 9.8. Here's the problem. And again, in my chart, it looks like it should be there, but that's because I've already done the work. In your chart, you will notice there's no information in this question that says what the delta Y, what the change in Y position of the cannonball is. Nothing actually tells us how high the castle wall is. Now, that's a bit of a problem because we're stuck. We don't have enough information to solve this problem based off of what we're told about with the launched cannonball. All right? So, we need to ask ourselves, is there a way we could figure out maybe the launch height based off of something else that's given to me in the question? And if we take a look at what it says, you'll notice that it also talks about, there's a reason I read about the other cannonball. It says the other cannonball was accidentally dropped, so it only has Y motion, and it takes 1.5 seconds to hit the ground. Why that matters is because that cannonball will have to go the same delta Y as the launch cannonball. Now that's a weird thing to think about at first, but at the end of the day, remember, these both start in the same height, and they're both going to end at the same height. So they both have the same delta Y. So if I use the information for the dropped cannonball, I should be able to calculate how tall the wall is. All right? So I start to write a Y chart for my dropped cannonball. The initial velocity is 0 because I drop it, so I let it go from rest. The acceleration, negative 9.8 because this is still in free fall when I let go of that dropped cannonball. And the time is 1.5 seconds. With those three things, I can solve for delta y, which is what I'm looking for. So I pick the formula that I need. All right. Because VI is 0, that first term goes away, and we're not going to have to use the quadratic formula for this part. So once I do that, I just simplify some more. Then I solve. All right. Go through, and we figure out that delta y, the change in y position of the drop cannonball, is negative 11.025 meters. All right. Now, that doesn't mean the wall is negative 11.025 meters tall. And that is a common mistake I see that I run into a lot. What that means is that the final position is negative 11.025 meters from the starting position. All right. And since the final position is at 0, that means that the starting position must have been whatever this first original height was. So the wall, based off of our work with the dropped cannonball, is 11.025 meters tall. Once I know that, I'm in business because I can take that value and I can put that in the launched cannonball chart because I know the launched cannonball is going to end up traveling the same delta y as the dropped cannonball. Again, it needs to be negative because this is measuring the change in the initial and the final, the change between the final and initial position. But now I know these three things. I want to find time. So I pick the formula that has that. Boom. This formula we used in the previous question. Unfortunately, because VI is not 0, we're going to have to do the exact same process we did before. So we plug in all our numbers. Nothing cancels out, unfortunately. So we move everything onto one side, so everything's equal to 0. Not unlike this. Now, once we do that, we ask ourselves, is there a way to solve it? And of course, there is. We're going to have to use the quadratic formula. All right. And again, if you don't remember what it is, hopefully you wrote it down somewhere. But honestly, there's a million different things online. You can just do a quadratic formula calculator, and it'll do all the work for you if you want to do that. But just remind yourself, this is A, this is B, this is C. If you plug into the quadratic formula, you should get something that looks like this. And then once you go through and solve it, again, you will have two solutions pop up. One will be negative, so you can throw that away because that is not going to work for us. That is not physically possible. The other one should be positive. And if you went through and did your calculations correctly, you should get that the time of flight that this object should go through should be 5.51 seconds. All right? Now, again, if you're still working through it, I'm going too fast, just pause the video at this point. Take some time to work through this part of the question. Once you're confident in the time of flight, unpause it and go to the third section. All right? So for the third and final part, now that we know the time of flight, we can figure out the maximum range or the range that it travels. Because I can take that time from the Y chart and I can put it in the X chart because that is what links them. Once I know that, I know everything I need to figure out delta X. All right? So I use our lovely formula, delta X equals the X velocity times time. I plug in my numbers. And I get that the X range, how far this cannonball is going to travel from the wall, is 238.58 meters. All right? Now, with these questions being completed, you now have the tools to work through just about any projectile problem. And you have the tools to map out how any projectile should fire. All right? Now, again, if you don't believe me or you still want to test yourself, open up the O physics thing. Open up that simulator, put in these parameters, and launch it. Because you should see your numbers should match up exactly with what you see in the simulator. All right. This one might go off the screen, I'll tell you. I haven't tried on the simulator, but this might go off the screen. So it might not be as simple to see. But what we're seeing here is just this idea. We can take these pieces, these tools we've kind of built over the past couple classes, and if we put them together in the right way, we can solve some pretty complicated questions. All right? So, if you have any questions, again, please don't hesitate to come to office hours. Feel free to shoot me an email. All right? Otherwise, have a great rest of the day, and I'll talk to you later.